Okay.
So stop sharing and then do your, go back to your presentation and make your presentation go full screen. No, no, don't share it yet. Go back to your presentation.
Oh. Oh, actually.
Correct, right there. So that one right there, and now maximize that to
Okay.
full screen. Now share it.
Okay.
I think that's what's happening.
All right. Well, let's see if that works. See? Share. Oh, all right. And red light blinking or recording. Make it good. So we're going to talk about digital integrated circuits. There's essentially, well, used to be just two families. There was the bipolar or TTL logic, and then they came along with CMOS, which was much lower power, um, which helped a lot as far as heat. We'll talk a little bit about the gates and programmable logic devices. There is a hybrid called BiCMOS, which is a TTL front end or a bipolar transistor front end with a CMOS output. So you get some of the low power from CMOS. I got it backwards. You get the high impedance or low input power for CMOS and the output power of a bipolar. CMOS devices don't typically carry as much power as you can do with a bipolar device. I've never actually used a BiCMOS device, but they are around. These are some typical circuits of what is in a TTL NAND gate or a CMOS, in this case, an AND gate, and how they're constructed. And you can see where the CMOS is all made with field effect transistors, and TTL is all bipolar transistors. So which of the following digital logic families has the lowest power consumption? D. I would go with D.
I would do it.
Because we didn't talk about ECL, which is emitter coupled logic, which is very fast, very high power. Schottky TTL was a version that was lower power and faster than regular TTL. And I don't know what NMOS is, but I'm sure it's a real one. So why do CMOS digital integrated circuits have high immunity to noise on the input signal or power supply? And I probably didn't talk about that. So what can we eliminate? We can talk about bypass capacitance. We can talk about bandwidth. No. So it's got to be Bravo or Charlie. And Charlie? That'd be a good guess. Because in CMOS, it kind of self-biases itself at half of the supply voltage. So in the case of TTL, it switches at, gee, I forgot. Around a quarter of the supply voltage. Normally it's 5 volts. So it'll be down around a volt or so, the switch. Where CMOS, because of the higher level in the middle. If you're operating at 5 volts, it's going to be over 2.5 volts to cause the output to change. So it has a little higher noise immunity. Which of the following is an advantage of bi-CMOS logic? So remember, that's the hybrid, which is a CMOS front end and a bipolar back end.
Well,
It's not, it's not B and it's not D.
let's see.
Yeah, I think it's a,
Yeah.
High input impedance, slow output impedance.
By the way, one of the things I was listening to about this stuff, can you go back to that real quick? All these choices are correct. There are some 70 questions on the pool that have that, and only in 16 of them is that the right answer. So if you don't know, don't pick that.
Okay.
Yeah, actually, we haven't come up with that all these are correct yet,
Right, there are a few, but there are very few.
which is not the case on the technician. There's a lot of all these are correct.
Yes, yeah.
Okay, tri-state. Normally, in a logic gate, you have two states. Okay, it's true or false. It's high or low. It's on or off. 1 or 0. They developed what they call tri-state logic so that you could connect multiple devices together to form like a data bus. So they have an extra control pin that allows you to put in what they call tri-state mode. It basically disables it, and it looks like a high impedance on its output. So it's effectively switched out of the circuit. So I can connect a whole bunch of them together, and as long as they're all tri-stated, the connection between them is all just undefined. If I turn one of them on, then that connection will be whether that's a high or a low. So it can pull it up or down. If I was to turn 2 of them on, one was high and one was low, they're going to fight one another. And it's going to wind up somewhere in between, depending on who has the most pull. So the idea is that you control the ones you turn on so you can actually make that what we call a data bus. So you can allow multiple devices to share the same conductor at different times. This is a kind of a truth table for a tri-state NAND gate. So it would be just like a normal NAND gate, except it's got this third input, which is the enable. So and you notice we use these little circles to represent inversion. That's why this is called a NAND as opposed to an AND,
not,
because it's an AND gate with the NOT on it. So it's a NOT in. And this is a NOT enable. So when it's a 0, the device is enabled. So it acts just like a regular AND gate or NAND gate. If I put a 1 on here, I'm going to disable it. So the output is undefined, is tri-state. So that's really the only difference, is you have that extra set of 4 states. So it doesn't care what the input is. The output is going to be
So you have a single scenario where you have a 0, which is when it's a 1, and a 0. Everything else is going to be like an on, right? Because you have an output of 1.
right.
But in the X's, basically all that's saying is just ignore this,
Right, it's like it's not there.
right? Okay,
The inputs don't have any effect on the output, and the output is going to be tri-state or high impedance,
mhm,
effectively disconnected.
right. Interesting.
So what is tri-state logic?
And no.
That was another hard one. When working with digital ICs, you need to know these different symbols. And the first one, number one, is a regular AND gate. Number two is the not AND gate, or we call it a NAND gate. Number three is an OR gate that has the curves, okay? And if we stick an inverter on the end, it becomes a NOR gate or a not OR gate. And then we have a device which is just if it didn't have the little knot or the circle, it would be a buffer. No, not a diode, a buffer.
Be a buffer.
Whatever you put in is what you get out. If it's a one in, it's a one out. A lot of times you use those to increase the current or drive, okay? If you have it with the inverter symbol, which most of them come packaged like that, like 6 in a package, and they're all inverters. So if you wanted to do straight through, you'd have to put two of them together. It inverts. So if you put a 1 in, you get a 0 out, or 0 in, you get a 1 out. And then you have number 6, which is not a real thing. I guess it's an alien spacecraft. I don't know. Or slice of pizza.
It's like pizza.
It does look like pizza.
So in 6.3, what's the schematic symbol for a NAND gate? In 6.3, what's the schematic symbol for a NOR gate?
D.
What's the schematic symbol for a NOT or an inverter?
C.
Okay. One of the things that you need to do when you're designing or building a circuit is if you have any unused inputs, you need to tie them, usually through a pull-up resistor, to a ground or whatever your positive source is. So you force it to a 1 or 0 state so the output is defined. If it's just floating, noise can cause it to switch back and forth, which can generate a lot of noise in the system. In the case of CMOS devices, they can get themselves biased in the middle, in the linear region, so it's on all the time, and heat up. And because the junction heats, resistance goes down, creates more current, and they can go into thermal runaway. What best describes a pull-up or pull-down resistor? Bravo. A comparator. This kind of a analog and digital device. It takes an analog input and creates a digital output. So it will have a threshold voltage, and when the input voltage exceeds that threshold voltage, its output will change, either from a 1 to a 0 or 0 to a 1, depending on how it's configured. In order to prevent it switching, like if say the threshold voltage on it was 1 volt, and you put a 1 volt signal on it, and it had a little bit of noise. So at one point it's 1.01 volts, and then it's 0.99 volts would be enough to cause that output to switch back and forth. Because it's more than 1 and it's less than 1. So what they do is they create what's called hysteresis. So once it switches on, once you exceed the threshold voltage, with the hysteresis effect, it's going to require a significantly lower voltage to switch off. Say the threshold voltage was half a volt. So if it's switched at 1, it's going to stay at 1 until you get below a half a volt. And you got the same effect going the other way. So the amount of that hysteresis voltage determines how much noise immunity you've got. So if you have noise spikes that exceed that, then you're going to get switching because of the noise. This is what one typically looks like. Kind of looks like an op amp. But the difference is you have and you can actually build them with an op amp. You have a reference voltage, which is what you set the threshold with. And then the input voltage you're going to compare to that reference voltage. And you're going to switch the output depending on whether it exceeds or it's above or below threshold. So what happens when the level of comparator's input signal crosses the threshold? B. What's the function of hysteresis in a comparator?
A.
What did you say?
I said A, alpha.
Yay for alpha. Okay, PLDs, programmable logic devices. In fact, probably everything nowadays, any complexity, is instead of built up with being built from actual logic gates, is made out of programmable logic arrays, where you program the logic, the actual gates. And they use a thing called hardware description language to be able to define that. And it's basically like a programming language where you can specify how you want the gates connected in that device, and then you burn or flash the device. And what it does, this is kind of a very simplex one, where you see these what look like fuses. They're actually fuses. In some cases, they're resettable. In some cases, they're actual fuses. And when you blow it, it's open. So you can control or make the configuration of that circuit depending on which of those fuses you open up. So if you want to have, and normally they'll have things like this input goes to both an inverting and non-inverting. So, if you want the inverted form of it, you pick that link and so forth. It's kind of a simplified example. They're much more complex than that, which is why you need the hardware description language to actually do it when you're talking about one with thousands of gates in it. So what is used to design the configuration of a field programmable gate array?
B.
Okay. I think we're done for today.
Wow,
Right.
you made it.
We only went over an hour over. But that's because the first part was kind of low.
That was difficult. I'm glad we did that.
Leadership.